Now, today we're going to continue on with listing out sample spaces for more than one trial. And yesterday we learned about two-way tables, which is a really useful way of representing the sample space for two trials. But sometimes we might have more than two trials, and two-way tables aren't very useful for that. So we want to use something that are called tree diagrams. So tree diagrams are useful for listing outcomes for two or more trials. Now, unfortunately, these can get very messy, especially if you have a lot of outcomes. So we're going to start with an example. And we'll start with 2 coin flips. And then I'll show you how to do the same thing if we had 3 coin flips. So 2 coins are flipped. Use a tree diagram to represent the sample space of all possible outcomes. Now, as the name suggests, a tree diagram involves branches and leaves. So if I'm talking about when I flip a coin, there are 2 possible outcomes. So when the first coin is flipped, there are 2 possible outcomes. Either I have heads or I have tails. We won't include the idea of the coin sort of landing on its side and staying there. These guys here are called branches. And these are called leaves. So my outcomes are leaves, and the number of branches represents the number of outcomes I have. Now, once I flipped the first coin, one of those 2 things happened. At the moment, I don't know which it is, but suppose I got a head. Then, when I flip the second coin, I could have a head or I could have a tail coming off of that. But what about if I got a tail on the first coin? Then when I flip the second coin, I could have a head or I could have a tail. So you can start to see why it's called a tree diagram, as this starts to look more and more like a tree, the greater number of trials that are involved. Now, a tree diagram is not finished until we write down our list of outcomes. There are 1, 2, 3, 4 separate outcomes. If you just look at the end point of each of those, it looks like there's only heads and tails. So we have to go back along our tree to see, how did I get to this heads? This was a head followed by a head. So I have to look back along the whole branch in order to find my outcome. Look back along the branch to find your outcome. So the first possible outcome is heads followed by heads, like that. How did I get to this tails? Well, I had a heads first, and then I had a tails. So this is head followed by tails. The third outcome is a heads in the second place, but before it I had a tails. Tails followed by heads. And this tails here had a tails before it. A tails followed by a tails. So my sample space is not the tree diagram itself, but rather this list of outcomes. My sample space, you remember the definition, is my list of all possible outcomes. So that's my sample space. Okay, not too difficult, but where tree diagrams become really useful, because we could have done this with a two-way table as well, is when we have maybe 3 trials, or even 4, but we won't go to 4. So let's see what happens if we had 3 coins being flipped. So for a second example, 2 coins are flipped. And we want to use a tree diagram. Use a tree diagram to represent the sample space. When you try and do this yourselves, you'll probably find that it gets a little bit difficult and gets a little bit messy. The key to tree diagrams and stopping them from getting too messy is the vertical line. You want your outcomes to be one on top of another. It doesn't matter if these guys have more or less space in between them. The important thing is that they line up going straight up and down. And you can use the boxes in your copy to help you do that. So here, my first coin, and I'm going to come all the way down here because I want to make sure that I've got lots of space above and below. This should be in the middle. So from the first coin, I could have heads or I could have tails. The second coin then. I apologize, guys. This should have said 3 coins. 3 coins are flipped. This is the point. So here I could have heads or tails. You can see they're in the same column. This one could have been heads or tails. And then my third coin, after this one, heads or tails, heads or tails, heads or tails, heads. And it's fine for the angles to be kind of stretched out like this, so long as we get all of our outcomes. And how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. And that makes sense because our fundamental principle of counting told us we'd have to multiply all the outcomes together. And that's why we have 8. Now, I didn't line these up particularly well. Let's list the outcomes. So my sample space is not complete until I've listed all of the outcomes. Let's go through each of these. This one was 3 heads in a row. Heads, heads, heads. This one, 2 heads and then a tails. This one, heads, tails, heads. This one, heads, tails, tails. This one, tails for the first coin, heads for the second one, and heads for the last. This one, you can see the pathway, tails, heads, and then tails. Second last, 2 tails followed by a head. And finally, 3 tails in a row. So that's my sample space of 8 different outcomes. Okay, so that's what tree diagrams are all about. Now, I don't want to give you guys any homework tonight because I want your test to be handed up tomorrow, and maybe some of you need the time to work on that, and I understand that. It's been probably quite a busy week. So I'd like you to try practicing with one right now. Excuse me. And here's the question I want you to practice with right now. So try now. And what you'll do, once you've taken this down, is you'll pause the video and then try it yourself. So what we have is a spinner that looks like this, and it has 2 possible colours. So we've got a spinner, has 2 possible outcomes. Green and purple. And I want you to take this down into your homework copy, complete this tree diagram. Okay, for 2 spins of the spinner. Okay, so for the first spin, we could have green or what. For the second spin, what would you fill in here? And it's just about practicing drawing them out and filling them in. So I want you to complete that tree diagram, and I want you to list the outcomes. So I want you to pause the video here. Everybody pause it, fill this in, and then press play, and I'll show you how we fill it in. It's very similar to what we've just done. Okay, great. So, of course, we would have had green or purple, green or purple, green or purple, and then the list of the outcomes: green followed by green, green followed by purple, purple followed by green, and purple followed by purple. Okay, so that's tree diagrams, and on Monday I will give you some homework on it, and hopefully you feel fairly confident with it. Excuse me. Now, moving on to the next topic, we're going to talk about numerical probability. Earlier in the week, we drew our probability scale and we wrote down some words describing different probabilities. And on our scale, we said that every probability was somewhere between impossible and certain, with an even chance in the middle. And we had unlikely and likely at the 1/4 and 3/4 mark. So now we need to learn how we would put some numbers on these. And it's very straightforward. Every probability is a number between 0 and 1. So we're going to write that down. Excuse me. It's a number between 0 and 1. Probabilities can be written 3 different ways. Well, any number between 0 and 1 is not going to be a whole number, right? So it can be written as a fraction, or you can write it as a decimal, or we can write it as percentages. And we learned before Christmas that those 3 things are equivalent, and we learned how to change one into the other. Now the question might tell you whether to use a fraction, decimal, or percentage, and if it doesn't, then any of those will be a correct answer, an acceptable answer. I'm going to use decimals for a probability scale here, but you could equally use percentages or fractions, whatever you prefer. And you'll remember from earlier in the week, this is sometimes called 50-50, and that's because it's using percentages. So the halfway point between 0 and 1 is 0.5, and we know that 0.5 is the same as 50%. It's another way of writing it. What's halfway between 0 and a half? Well, we can just divide 0.5 by 2 and get 0.25, or that's also a quarter or 25%. What would we fill in here? 0.75, 75%, or 3/4. Now, this allows us to represent probabilities all between all of these different labels that we have. So we can compare whether things are more likely than each other, even if they're quite close together, because we can put an exact number on them. So this is really important to know. Now, I want to write down a definition for how we calculate numerical probability. Calculating numerical probability. How do we do it? Well, we have a formula. We say that the probability of an event, so that's an odd looking notation. I'll come back to it in a second. The probability of an event occurring is the number of outcomes that match that event It's a really long sentence. So the number of outcomes that match that event divided by the total number of outcomes. Okay, let's just make a note on this notation here. So P bracket big E like this. P of E. This means the probability of an event. This will make a bit more sense when we do an example with it. Now, this is too long, right? We don't want to be writing this down every time. So instead, I prefer to write down our formula like this. The probability of an event, and that's how we pronounce it, even though we write it with shorthand like this, is the number of matching outcomes divided by the total number of outcomes. So that hashtag symbol there, the cardinality symbol, as we remember from sets, means the number of things. So it's the number of outcomes that match our event divided by the total number of outcomes, the size of the sample space. Let's do an example to show what that means. So I'm going to keep that there for us to see. Now, so for example, if we roll a 6-sided dice, a 6-sided die is rolled. 1, list all possible outcomes. And calculate the probability of getting a value greater than 4. As a reminder, do we include 4 when we say greater than? We don't, right? Okay, that will be greater than or equal to. So we're not going to include 4 when we list the things that are greater than 4. Okay, let's do the answer. So when I roll a 6-sided die, standard 6-sided die, the outcomes are the numbers 1, 2, 3, 4, 5, and 6. And then calculating the probability. So the probability that I get a number greater than 4. You can see this is the event, getting a number greater than 4, and the P outside it means the probability. Well, it's going to be a fraction that's calculated by the total number of outcomes. What's the total number of outcomes? 6. So 6 is my number that goes under the line. And I said, on top, I say, how many matches do I have? Well, to be greater than 4, 5 and 6 are the possible matches. And there are 2 of those. So it's how many I have. I don't put 5 and 6 over 6. I say, I count them. I've got 1, 2 matching outcomes. So 2 out of 6. And I would simplify that, because that's an equivalent fraction, to 1/3. And that's my answer. Okay, so that's how we calculate probabilities. And you'll know if you've made a mistake, if you ever get a number that is not between 0 and 1. Right, like I said, I'm not going to give you homework tonight in this. We'll do a few more examples with calculating probability on Monday, and you'll have homework then. And let me know if you have any problems with doing the open book test and uploading your answers. So thank you very much, and I will talk to you on Monday. Have a lovely weekend, and thank you for your hard work this week. Bye.